Welcome to the third lecture of the series on supramolecular chemistry. Today I will discuss about the intermolecular interactions. But as we know that whereas in traditional chemistry it concentrates on the covalent bond, in supramolecular chemistry it examines the weaker and reversible non-covalent interactions between the molecules. And usually these forces include the hydrogen bonding, metal coordination, hydrophobic forces, van der Waals forces, pi-pi interactions, and different electrostatic forces or effects, whatever we see. So this topic is very important for NEET, IIT JAM, GATE, CSIR NET, BPharm, BSc, MSc students, and for their organic chemistry exam papers. So let's start with the electrostatic interactions. There are several specific interactions which falls under the heading of electrostatic interactions, like as you can see over here. I can read out those: ion-ion interaction, ion-dipole interaction, dipole-dipole interaction, hydrogen bonds, halogen bonds, cation-pi interaction, and also the pi-pi and charge transfer complexes, which I will talk as well, besides the electrostatic interactions. So before we proceed to individual interactions, this is a general outline for understanding or for the comparison of the interactions that we will talk about, like their strength and some of the examples or a representative example of each kind of interactions. As you can see here in the ion-ion interactions over here, we can just have the highlight or pen. Here the ion-ion interaction, you see the strength in kilojoule per mole for such kind of interactions falls between the 100 and 350 kilojoule per mole. And one of the representative example can be seen as tetrabutyl ammonium chloride, where this ion-ion interaction exists. Also, then it comes the ion-dipole interaction, which have the strength in 60 to 200 kilojoule per mole, depending on the substrate nature. Like here sodium 15 crown 5 can be seen, or that means the sodium crown ether complexes falls under this category. Another interaction is dipole-dipole interaction, very important one, as you can see in acetone molecule, and which have a little less strength in terms of a 6 to 60 kilojoule per mole. Another one, very important one, is the hydrogen bonding, having energy between 4 to 120 kilojoule per mole, and can be represented as the donor of the hydrogen atom, the hydrogen atom itself, and the acceptor of that one. That then we know that the donor and the acceptor that need to be electronegative atoms, and I will come into the definition and further discussion on these things. Another one is the cation-pi interaction, having less energy compared to the others, and its energy fall in the range of 5 to 80 kilojoule per mole, depending on the substrate nature. And for example, this one can be treated as the potassium ion in benzene. Pi-pi interactions can have energy between 0 to 60. Examples are benzene or graphite. Van der Waals interactions, which are much less in energy content, having energy of less than 5 kilojoule per mole, and it depends on the surface as well. The examples can be the argon or molecular crystals. Another one is the solvophobic interaction, which depends on the solvents, purely on the solvents, and we can find its role in the cyclodextrin inclusion compounds. So these are several interactions which are found in the supramolecular chemistry, the intermolecular interactions. Now we will go into detail of the electrostatic interactions as I showed in the previous slide. The first one comes the ion-ion interaction, and these ion-ion interactions are an attractive force between the ions with opposite charges. They are also referred to as ionic bonds and are the forces that hold together the ionic compounds, like the charges repel each other and opposite charges attract. Okay, so but as we know that the like charges repel and the opposite charges attract, and these coulombic forces actually operate over relatively long distance in the gas phase. So this is very important to understand the phase in which they are more prominently interactive or showing their existence. Okay, A representative example, as you can find here, can be seen as the sodium chloride, and if you can find the 6:6, the structure of the sodium chloride, the energy falls in between the 100 and 350 kilojoule per mole, as mentioned in the previous slide as well. Another example for this one, which is observed in the ionic liquid crystal, is the ammonium salt, as mentioned, where it can be the fluoroborate salts, and this molecule shows the liquid crystal behavior, the supramolecular, new supramolecular behavior, which is definitely addition to a molecular chemistry, that the liquid crystal property was found for this kind of interactive um, nature or interactive character in these molecules, which enables the molecule to show the liquid crystallinity within the range of 0 to 200 degrees centigrade. So this is a very important phenomena of this ionic liquid crystal. We can then move to the ion dipole interaction, and here in the ion dipole interaction, you can find, I have shown here several examples, like the hydrate of sodium plus, the octahedral structure, where sodium plus is surrounded by water molecules in the octahedral orientation, and also the sodium crown ether complex, where you can see the 18-6 sodium complex, as well as the rubidium bipyridine complex, you can see over here in the third example, and also the steel vessel you can see here, and it shows also the liquid crystallinity within the range of 165 to 234 degrees centigrade. So this molecular phenomena or characterization that's been incorporated into the supramolecular chemistry and the outcome of supramolecular chemistry, we can say. So these are the ion dipole interactions example in these four representative examples here. Okay, and definitely I have earlier mentioned also that the energy of such kind of interactions can vary from 50 to 200 kilojoule per mole. Okay, so this is in terms of the energy within the molecule. Next comes the dipole-dipole interaction, and as we can see that the dipole-dipole forces are the attractive forces between the positive end of one polar molecule and the negative end of another polar molecule. Okay, so this is the manifestation of the dipole-dipole forces, and in dipole-dipole interactions, the molecule with permanent dipoles attract actually each other electrostatically. The positive end of one molecule attracts the negative end of another molecule, and so on, leading to an alignment of the whole molecules. Here, two representative examples have been shown with the carbonyl compound first. Here, the orientation you can see in the type 1 and type 2, like here, if the two carbonyl compounds are oriented in type 1, then this is the electrostatic interaction or the dipole-dipole interaction in such a way, and in another type, which have in energy is quite less compared to the overall range of 50 kilojoule, it's in type 2, it's about 20 kilojoule per mole. So we can say that the dipole-dipole interaction ranges between 5 to 20 kilojoule per mole when we talk about the orientation of the carbonyl compound in such a way that it's the anti-orientation leading to more stable structure in type 2, or the more stable interaction rather to say. And also it can be the dipole-dipole interactions can be found in substituted aromatic building blocks. Here you can see the hydrogen atoms have been substituted with different functional groups like halogens, cyano group or nitro groups, and leading to different dipole moments of the whole molecule, and thereby creating the option of dipole-dipole interaction within the molecule. Okay, so these are manifestation of the dipole-dipole interaction within carbonyl compounds and also the aromatic compounds as well. Then comes the very significant ones is the hydrogen bond, which have energy usually 4 to 100 kilojoule per mole. Here you can see an example of the dimers of carboxylic acid. But before I move into the discussion around this, we need to understand that a hydrogen bond is a primarily electrostatic force of attraction between a hydrogen atom, which is actually covalently bound to a more electronegative atom or group, and another electronegative atom bearing a lone pair of electrons, which is said to be the hydrogen bond acceptor. Okay, so here if you can see here in terms of the representation of these carboxylic acid compounds, you can see that the Lewis acid electron pair acceptor and the hydrogen bond donor for this molecule, this oxygen atom, will donate this hydrogen atom, and here this oxygen acts as the Lewis base, the electron pair donor, and the hydrogen bond acceptor. Reversely, the other part of the molecule, this goes the other way around for the same hydrogen bonding. So in hydrogen bonding, the interaction involves actually the hydrogen atom located between a pair of other atoms having a high affinity for electrons, and generally in such a bond is weaker than the ionic bond and covalent bond, but these are obviously stronger than the van der Waals forces, of course. So hydrogen bonds are stronger than van der Waals forces. We must understand that thing. Let's see another example. So this is the manifestation of the dipoles and how the interaction takes place, and it can also be regarded as the dipole-dipole interaction if you can look in that way. So there are poles generated because hydrogen atom is attached with an electronegative oxygen atom, thereby creating a dipole within the OH bonds. Next, another example, we can see the dodecyloxy benzoyloxy benzoic acid derivative, so abbreviated as DOBOB derivatives, which is shown over here. Now you can see here, if the hydrogen atoms be here, if the hydrogen atoms, this is hydrogen atom, then the molecule is showing the liquid crystalline behavior, as you can see over here, that the hexagonal columnar, this col H, that means the hexagonal columnar mesophase, that is the liquid crystal structure of the whole molecule, this dimer molecule, when there is hydrogen bonding. Now if we break the hydrogen bonding by means of putting a R group instead of hydrogen, so if this H is methyl group, that means there is no option for any hydrogen bonding, then this becomes mere a crystalline structure having a melting point of 65 degrees centigrade. So we can understand how important in hydrogen bonding by for the inclusion of a new property of liquid crystallinity in a dimer structure of carboxylic acid derivatives. Okay, so if this is only H is only R or methyl, this is simple crystal. If this is hydrogen atom, which makes it enables for the hydrogen bonding, the intermolecular hydrogen bonding between this structure, leading to the formation of liquid crystalline structure within the molecule. So this is a very important manifestation of the significance of hydrogen bonding. And now, what is the special about the hydrogen bonding? Why this is capable of exerting incorporation, inclusion of new characteristics into the supramolecular structure? Now, if we look that the uniquely small size of the hydrogen atom that allows hydrogen atom allows the strong interaction of a positively polarized hydrogen atom with nearby electronegative atom, and also the high bond dipole moment of the XH bond, because if you can see the X molecule atom being the electronegative one, like oxygen here, and these hydrogen atoms, so this the high dipole moment, because oxygen is so very electronegative compared to hydrogen atom, so the dipole moment of the XH bond is very high. Also, the short distance of the XH intermolecular bonds that leads to the formation or the this kind of unique structure within the molecules. And if you look at the directional point of view, the high electrostatic interaction energy of 10 to 40 kilojoule per mole for this kind of bond, and the directional bonding, the alignment of the dipoles between the, because this is quite fixed, that hydrogen atoms have to be flanked between two atoms, both of them had to be the electronegative atoms. if we look at the directional property or directionality of the amide-amide hydrogen bond in proteins in solid state, we can have a look in the structure here. This is the amide hydrogen bond when hydrogen is attached with nitrogen atom, and further it can make the hydrogen bonding with oxygen atom of another amide molecule. Okay, so this is the manifestation or the directionality of the amide-amide hydrogen bonding in protein, because in protein it's about the amino acids, and therefore we can conclude that the hydrogen bonds are the master key interaction based on their relatively strong and highly directional nature. So these 2 point, that the relative strong in character and highly directional nature, that makes the hydrogen bonding to impart a significant role in incorporating new characteristics or supramolecular chemistry. There is a rule called Etter's rule regarding the hydrogen bondings, and it states the 3 points are there. It states that all good proton donors and acceptors are used in hydrogen bonding, and the 6-membered ring intermolecular hydrogen bonds form in preference to the intermolecular hydrogen bond. Uh, then the best donors and acceptors remaining after intermolecular hydrogen bond formation form the intermolecular hydrogen bonds to one another. So these are 3 points need to be reminded as well. Now, there is a manifestation or representation of hydrogen bonding in materials science, very importantly, like in intermolecular hydrogen bonding as well, and the intermolecular hydrogen bonding as well. You can see over here in the 2 representative structures how this intramolecular hydrogen bonding in the first figure A shows that how it lead to the helical structure in the molecular orientation in a unit cell of this bulky molecule. Okay, so this is a representation of a unit molecule. Here you can see this is the unit molecule representation, this one. And now when this aligns within the unit cell in the molecular structure, it gives the opportunity to make it a helical structure into the unit cell, and thereby leading to the some beautiful phenomena or characteristics within the molecular structure. Whereas the intermolecular version of hydrogen bonding in material science, that can be shown here in the terms of these hydrogen bondings in the stacking direction is shown over here as well. And you can see here the helical structure when it forms the intermolecular bonding into the columnar structure. You can see the columns like here, and this is a hexagonal columnar structure, and the helical orientation is shown in the direction helix 1, helix 2, and helix 3 are directed accordingly, and this is a unit manifestation of the stacking direction of the molecules within the molecular structure. Next comes very important, the 5th one is the halogen bonds. Usually a halogen bond occurs when there is evidence of a net attractive interaction between an electrophilic region which is associated with a halogen atom in a molecular entity and a nucleophilic region in another or the same molecular entity. So this is a general representation of the halogen bonding, and in terms of attraction, halogen bonding is the attractive non-covalent interaction, and it can form between an electrophilic region, as I said, of a halogen atom in a molecule and a nucleophilic region of a molecule in the same entity or other molecular entity. Now this bonding can be exploited in areas such as supramolecular chemistry and crystal engineering, and also for the fabrication of the liquid crystals. So in that aspect, halogen bonding are very, very important, and the energy associated with such kind of bonding, as you can see over here, is around 10 to 200 kilojoule per mole. So this is quite a imparts good bond. And here a representation over here, yx in addition to D makes YX and D. So here the Lewis acid halogen bond donor is Y, and this is the D is the Lewis base, which is basically the halogen bond acceptor, and this makes this halogen bonding. And the strength of the halogen bonds are are descending in the order of sp-cx bond greater than sp2cx bond greater than sp3cx bond. Okay, so this is the descending order of the strength of halogen bonding in the molecular structures. So here are a couple of examples, and we can understand how halogen bonding gives incorporation or inclusion of a new phenomena or structural characteristics within the molecular or within the supramolecular structure. For example, here we can see the molecule which is not liquid crystal and a colorless molecule here, this olefinic molecule. Now if you add this the iodo pentafluoro iodo aromatic compound, then the halogen bonds get formed, and in that case it gives the molecular structure, the liquid crystal structure. Like here you can see from crystal to smectic A, which is the liquid crystal phase, to the isotopic phase, and from the colorless it become slightly yellow in color by the addition of another the iodo and pentafluoro benzene moiety, this one. So by means of halogen bonding, liquid crystallinity has been incorporated or introduced within the molecular structure. So if we add, instead of iodo compound, add some pentafluoro bromo benzene derivative, then the no liquid crystal due to the reduced polarizability of the bromine atoms. So that means the CX, the polarizability of the CX bond here, the liquid crystallinity is available in case of CI bond, whereas when the polarizability reduces with CBr bond, so the polarizability of this bond is very important, as it is more compared to this CBr bond. This one lead to the liquid crystalline structure, which is not possible or which is not favored in case of pentafluoro bromobenzene derivative. So this thing also need to be memorized or need to be understood. Next comes the cation pi interactions having energy in between 5 to 80 kilojoule per mole in the range. Here the transition metal and the with the pi bond, you can see with the ferrocene derivative with the Zeiss salt. These are the examples of cation pi interactions, and these are mainly in that sense these are mainly covalent in nature. And another important example is the interaction of potassium ion with benzene. This interaction with benzene in the gas phase having energy of 80 kilojoule per mole, whereas in with the water molecule also in the gas phase, it's having energy of 75 kilojoule per mole. So you can see a schematic representation of the cation pi interactions over here, where its interaction shown here with the potassium ion with the benzene molecule. And if you can see in that sense, in the right hand side, the schematic representation, the right hand side representation here, this one, if you can go through this one, this is a manifestation of the cation and the pi interaction. The orientation of the pi bonds can be shown in the black over here. This is the orientation of the pi bonds, and the cation can have interaction with the pi bond of the benzene ring. So in the gas phase, the interactions are having quite higher energy. Okay, now we come to the pi-pi interaction and the charge transfer complex, the last one, as mentioned in the very beginning, that the repulsive and charge transfer interactions are quantum mechanical, and it depends on the exchange integrals, and it has to be considered as a very weak chemical bonding according to the perturbation theory. Now you can see in the two boxes here, the left one shows the repulsive forces by means of representation in the homolumo interaction. The attraction generates from the van der Waals forces, whereas in case of charge transfer interaction, for example in the EDA complex, you can see the charge transfer interactions with the trinitrobenzene and with the benzene, and also you can see the homolumo interaction or the molecular orbital interactions, where we can see the change in enthalpy is -8 kilojoule per mole in vacuum. So this comes, the calculation comes from the homolumo interaction, and in case of trinitrobenzene, which will have a very lower homo compared to the benzene because of the presence of 3 electron withdrawing nitro groups. And then in the molecular structure, you can see the orientation or the transfer interaction uh, here, showing the pi-pi interaction and the charge transfer complex from the benzene and the trinitrobenzene, and the pi-pi interaction in two benzene molecules over here. Another manifestation of the pi-pi interactions, which have energy of 10 to 50 kilojoule per mole, is when it can be manifested in terms of the face-to-face interaction or edge-to-face interaction. Okay, like in the face-to-face interaction, which having the spacing distance between the two molecules of benzene is 3.2 to 4.5 angstrom, and the orientation here you can see over here the orientation. This is a repulsion over here, and these are the the orientation of the pi bonds over the benzene ring, and how the attraction can take place as well. So this is the manifestation of the repulsion over here. This part shows the attractive interaction. A molecular representation shows here where the internal aromatic core uh, acts as a rigid core, whereas the alkyl sulfur chain, which is the flexible chain in the molecular structure, that shows the flexibility in the molecule, and that is that is an example of the face-to-face interaction within the molecular structure. Whereas if we go with the edge-to-face interaction of the pi-pi interaction, this is the edge of one benzene ring, this is the face of the another one. If we go with the edge-to-face interaction, that may lead to the attraction, and it's kind of the herringbone structure you can see with the 613 dihydrodiazepentacene in that molecule. So this is generally known as the herringbone structure. So we need to learn this process, and we need to learn this nomenclature, and this comes for the edge-to-face interaction of pi-pi interaction. And for face-to-face interaction, I have already mentioned. Then comes another example of the charge transfer complexes, where the electron, basically this is the electron donor acceptor complex. Here two molecules are there, the rigid aromatic core containing the six the alkoxy chains around the periphery of the molecule, and here with the trinitrofluorinone being the guest molecules. And if we can see the interaction, that the induction of the columnar assemblage with a minimum content of 25% of TNF is necessary. So if the molecular structure is like that, a graphical representation may show you that the orientation of the columnar assemblage like that fashion, and then comes the TNF. When insert into the molecular structure, in the red part you can see that the TNF molecules, that shows the stacking of the columns, and hereby the charge transfer is getting facilitated into from the donor to the acceptor molecule. Okay, so this is a very interesting phenomena or example of a charge transfer complex with the rigid core aromatic structure and TNF molecule. Another example of this charge transfer complex you can see over here, and this is the structure you can see with the TNF and tetra-substituted benzene cores with the ester substitution, and with the perilene as and the terminal attachment, and the orientation can be seen in that fashion. This is a molecular representation or the modeling of this compound, showing the orientation in the charge transfer complex. And in presence of the TNF, when we see the complex in presence of TNF, then the texture is showing the liquid crystalline character at 93 degrees centigrade with the smectic A phase, and the palladium complex and TNF in a 1:2 ratio. It shows this liquid crystalline behavior. So these charge transfer complexes are very important in exerting also the liquid crystallinity within the molecular architecture. So thank you very much for watching TG Chemistry. Keep watching, and don't forget to subscribe my channel if you like the video, and press the bell icon to get more videos which I will upload in future. Thank you.